Good day. I am going to talk about graphene-based integrated photonic devices. Our cameras today are able to capture the most beautiful and detailed images, but what if we could see beyond the visual spectrum? Researchers from the Institute of Photonic Sciences in Barcelona, known as ICFO, one of the leading establishments in graphene-based optoelectronics, released a journal entitled Broadband Image Sensor Array based on Graphene-CMOS integration, where they explore the superb optoelectronic properties of graphene and quantum dots in unlocking the infrared spectrum for digital cameras everywhere. Cousins et al. Created a 388 by 288 pixel array of graphene colloidal quantum dot photodetectors that operate as a digital camera with increased sensitivity for visual and infrared light. Assembly first involves the transfer of graphene onto a complementary metal oxide semiconductor, or CMOS die. The graphene is then connected to readout integrated circuitry, or ROIC, through vertical metal interconnects. Lastly, a sensitizing layer of lead sulfide colloidal quantum dots are deposited via spin casting. The mechanism of photoresponse is based on the photogating effect, which is the light-induced change in carrier density and thus conductance. The quantum dots that are sensitive to UV, visual, and IR absorb the light, and a built-in electric field generates the electron-hole pair. Photo-generated holes then transfer to graphene and circulate because of bias voltage. A capacitive transimpedance amplifier in the ROIC integrates the change in current between the photosensitive pixels and the blind pixels. The sensor is able to produce several images containing visual, near-infrared, and/or short-wave infrared light, depending on the light source and filters used. Figures G and H reveal that both fog and silicon are transparent in short-wave infrared light, while figure I shows how water absorbs short-wave infrared light. Optoelectronic characterization revealed that within the area covered in graphene, 99.8% of pixels had resistance, or in other words, were functional. Inset shows a 10 by 10 pixel area with each pixel exhibiting approximately 20 kiloohms of resistance. Graph K shows that the compensation resistor in the ROIC optimizes and calibrates each pixel so that the average resistance is 20 kiloohms and thus within the operation regime of the ROIC. Figures L and M describe the dependence of the detector signal on the irradiance experienced by each pixel. Up to 95% of pixels are sensitive to irradiance corresponding to partial moon and twilight conditions in the visual spectrum. Figure M compares this study with other photodetectors. There is a vast number of high-performance and ultra-sensitive gadgets that utilize the superb optoelectronic properties of graphene and other 2D materials. But this research provides the first monolithic integration of photodetectors in readout system. As a digital camera, this is also the first of its kind to have a spectral range involving infrared. However, the real gems of this study are the colloidal quantum dots, because the spectral response of the sensor can be altered by modifying the type and size of quantum dots used. The figures shown here illustrate the spectral dependence of the photoresponse of pixels of the ROIC sensitized with quantum dots. The first figure utilizes a quantum dot with exciton peak at 920 nanometers, or near infrared, while the second figure pertains to a quantum dot of exciton peak at 1670 nanometers, or shortwave infrared. Figure B also shows a detection sensitivity that ranges from the visual region all the way to 1850 nanometers into the IR region. Inset shows the absorbance spectra of the quantum dots in solution. Now we look to this patent application filed by Lee et al. Entitled Optical Sensor and Image Sensor Including Graphene Quantum Dots. Similar to the study by Cousins et al., it involves the use of graphene, but rather than combining graphene and lead sulfide quantum dot layers, it uses graphene quantum dots as photodetectors. Moreover, it involves the functionalization of graphene in its optical sensor layers. Using the technology discussed in this research, as well as the usual RGB model for visual range cameras, a high-resolution broadband infrared camera can be constructed. Simply by changing the type and size of quantum dots, we can customize their sensitivity to certain wavelengths. Additionally, shortwave infrared can be used in broadband applications such as fog or night vision modes in automobiles. On the other hand, near-infrared can also be used as a narrowband tool that determines the freshness of produce. Thank you.